Hello Year 13 and welcome to Spectroscopy, particularly NMR spectroscopy. This is my favourite bit of the A-level course, and it's also NMR is my chemistry specialism, so we should be looking to have a lot of fun with this. As well as my own excitement, and I'm sure all of your excitements, this is an area that's really easy to score marks on in an exam, because you get quite long 10-mark questions, and if you can get your head around the signing NMR spectrum, you can score a lot of points that most other candidates are going to stumble over. So it's a good place for us to differentiate ourselves from other candidates. Now I've split NMR into two. We're going to do carbon NMR today and a little bit of background, and then once we're feeling more confident with that, I'll move us on to proton NMR, which is a little bit more complicated. So here are all the specification points for NMR. You can see there is an intimidating number, but we're just going to cover the first two today, and also we're going to cover E. We'll be covering bits and bobs of some of the other ones, but we're not going to be covering them in full until we start looking at proton NMR. Okay, so a little bit of background first. As you remember from AS, all the electrons in an atom are sitting on energy levels. I'm not sure though if any of you ever thought about what that actually means. Well, the energy levels are discrete amounts of energy that an atom or an electron can have. For these ones are the electrons, and they cannot have any energy that is not one of these levels. Now what that means is, if you imagine having a car that could only go at either 50 miles an hour or 60 miles an hour. It couldn't go at 55, it could only go at 50 or 60. That's kind of what this is like. So in order to get it from 50 miles an hour to 60 miles an hour, you'd have to give it exactly the right amount of energy to bridge the gap between 50 miles an hour and 60 miles an hour. Electrons are exactly the same. If you hit them with some energy, some light with the correct amount of energy, it will move them from one energy level to the next energy level. They'll stay up there for a little bit, and then once they're done up there, they'll fall back down to their original position, and they'll give out the energy that was given to them originally as light, or well, as radiation, electromagnetic radiation. And that radiation gives us information about the state of the atom. It tells us what's going on there, what's happening. And that's the basis for all spectroscopy. Energy goes in the form of light. The atom or electron changes its state, moves from one energy level to another energy level, drops back down and gives out the light. We read the light and it tells us about the distance between the energy levels. That is the essence of quantum mechanics. So what about NMR? What is that? Well, as we know, or may remember from AS, electrons are magnetic. They can either be up or down, as in terms of where they're aligned with their poles. Some nuclei are magnetic too, only some. Tends to be ones with odd numbers of protons or odd numbers of neutrons. If you put them in a magnetic field, these nuclei, so here's our nuclei, they're magnetic, these are their spins, their little magnetic fields. Sometimes some of them are going up, some of them are going down. Now if we put them in a massive magnetic field, it's going to require, the lower energy state is going to be when the little nucleus is lined up with the magnetic field that we're applying, because otherwise it's having to fight against our magnetic field, which is much larger. Now that means we've got two states, be up or down. And if we hit the atom with some radio waves, we can make it change its orientation to be against the magnetic field. It will then flip back once we've stopped hitting it with radio waves and release the energy back to us, so we can see how much energy it is required to flip the nucleus. And that is exactly how an NMR machine works. An NMR stands for nuclear magnetic resonance. So we just saw that the nuclei are magnetic, and then we just saw them resonating between the two states, between up and down. We have a big magnet, so this is all it is, and this is all you need to know about how an NMR machine works. You have a big magnet. Inside it you have some radio waves, a source of some radio waves, and then something detects the radio waves that are emitted from the atoms. This is a very large one. and you can see in the background there is another smaller one over here. So, which nuclei are magnetic? Well, thankfully, both hydrogen 1, which is the most abundant element in the universe, and carbon 13, which is not very abundant, but very abundant within organic molecules, are magnetic. Now, carbon 13, only about 1% of carbon are carbon 13 nuclei, as are of the carbon 13 isotope. But that, if you think about there being 6.0 times 10 to the 23 atoms in a mole, there's enough of these carbon 13 nuclei around for us to find them. We're going to look at carbon 13 today and how we can do NMR on it, NMR spectroscopy. So, carbon 13. NMR spectroscopy, carbon 13 NMR spectroscopy gives us two main pieces of information about our molecules, because that's what we're trying to do here. We're trying to find out what's going on with our molecule. What molecule is it? The number of different carbon environments on the molecule, and then which atoms are bonded to those carbons. And to be honest, that's quite a lot of information. That's more information we've been able to get from any analytical technique so far. Now, carbon environments. This is a new concept, so I'm going to take a little bit of time over this. Not all of the carbons are the same in an organic molecule. That's quite obvious. You could point at one. I could take an organic molecule. You could point at one, and then I could blindfold you, move it around, and you would be able to point at the carbon you had pointed at originally, based on which atoms were bonded to it. Even if they look like they have the same atoms bonded to them, sometimes the carbon chain attached is different. So even if they've got all the same atoms bonded to them, if the carbon chain is different that is attached to it, you would still be able to pick it out if I spun it around with while you had your eyes closed. So therefore it is different. So we're going to have a look at how to spot the carbon environments here. First molecule we're going to look at is ethane up here. Now, this carbon has got 3 hydrogens and another carbon bonded to it, as has this one. Clearly, they are the same. You would not be able to identify which one you had pointed to originally if I spun it around. So, there's only one environment. We're going to label that environment A, and this is the notation I want you to use every time you are labeling carbon environments or hydrogen environments. Put all of the ones that are the same, give them all the same letter. Write the letter on the molecule just so you're clear. Okay, so we have 2 carbons, environment A. What about propane? Well, we have this one on the end. Then we have, which has 3 hydrogens and 1 carbon attached to it. This next one has 2 carbons, each attached to 3 hydrogens, and 1 and 2 hydrogens attached to it. So it's clearly a different environment. You would be able to point that one out if I spun around the molecule. So we're calling that B. Now this one is attached to exactly the same thing as this one. You would not be able to tell the difference between these two if I spun the molecule around. It has 3 hydrogens and then a 2 carbon chain attached to it, exactly the same as this one. So we're going to call that one A as well. Right, let's look at ethanol. In ethanol, we have one environment here, and clearly a second environment here. Finally, we're going to look at methyl propane. So, start off as we did with propane. One environment here. Second environment here. These two are different. Now, these 2 environments are the same. We can see that they're both bonded to a 2 carbon chain and 3 hydrogens. But so's this one. This one's bonded to a 2 carbon chain with a methyl group. This one's bonded to a 2 carbon chain with a methyl group, and so's this one. You wouldn't be able to tell the difference between the 3 of them if I spun the bonds around. If I rotated all the bonds, you would not know which one was which. So even though they're not, you can't reflect them onto each other like you could with these 2. This carbon is the same as this carbon, which is the same as this carbon. They're all environment A. Okay, so we've found out how many environments there are. The other piece of information is called the chemical shift. So each environment translates to 1 peak on our NMR spectrum. Spectrum is just like a long graph. We're going to look at some in a minute. And we measure where these are by what's called the chemical shift. They will be shifted away from 0. So they'll have a number associated with them. We label this number with a little delta, a lowercase delta, and it's measured in ppm, or parts per million. Don't worry why it's called that. Just know that it is. Now the amount they're shifted away from the 0 depends on a couple of things, but for most of the molecules you're going to be shown, it's going to be due to how electronegative the groups bonded to the carbon are. The more electronegative they are, the more downfield it's going to be shifted, and by downfield I mean more to the left. Let me show you what I mean. So here we have two NMR spectra. One for ethanol, one for propane. Now, I've labelled these the two environments as we did before. You can see there's two peaks for the two environments. We were right. One of the carbons is bonded to oxygen, the other one isn't. So, quite clearly, this carbon, which has a chemical shift of around 60 ppm, is attached to a more electronegative group than this one, which is shifted about 19 ppm. So when I say when they're shifted downfield, what I mean is it's got a bigger number towards the left. It's moved by a larger amount to the left, to this peak. Everything we take relative to the 0, so this is more left than the 0, than this one is left than the 0. So we can say that this one must be the environment B, and this one must be environment A. Now let's look at propane. It might look like these two are more downshifted, but the eagle-eyed among you will have noticed that the scale is different, and this is just 16, so this would be about here on this spectrum. So the oxygen on here has even made this carbon A shift downfield a little bit. You'll notice there are two peaks because there are two environments. Now I wouldn't feel comfortable trying to work out which one of these two was more downshifted than the other. They are very close together. However, there are two carbons in environment A, and this peak is twice as tall as this peak. So we can use that to work out that this carbon must be twice as abundant as this one, therefore this one must be carbon A, and this one must be carbon B. Okay, the final thing we're going to talk about today is what this 0 on the graph is. All the NMR measurements are taken relative to a compound called tetramethylcyanine, which is here. So that's just a silicon atom with 4 methyl groups attached to it. So a few reasons we use this as our 0. One, all 14 hydrogens and all 4 carbons are exactly equivalent. So it just gives one massive peak. It's completely unreactive, so it won't react with your sample. And silicon is very, very not electronegative. It is less electronegative than carbon. So it actually means that it's going to be the highest chemical shift you'll ever see, the most to the right of the chemical shift spectrum than you'll ever see, because it's so unelectronegative. Now that was a very strange use of language, but essentially I'm sure you'll get what I mean. Because this is so electropositive, that's the opposite of electronegative, everything else, every other compound will be downfield of it, so everything will be the same side of the 0. Okay, hopefully you've bore with this so far. Now, the two main things I really want you to get out of this are how to spot chemical environments and how to assign chemical shifts, how to work out what the chemical shifts are. Don't worry about remembering chemical shifts, because you will get given in your on your data sheet, you'll have some chemical shifts for both carbon NMR and hydrogen NMR, some common chemical shifts, so you don't need to worry about working it out using electronegativities. You can just look at the numbers that it says in the data sheet there will be.